rather than the mouse pointer. So I'm Thomas. I'm currently a third year PhD student at HKU. I use Scala from time to time, um, and I contributed to Scalding a while ago as a part of Google Sem of Code. I have one sort of note of warning, so I prepared these slides in Jupyter. If you're familiar with it, so it's originally for Python. It's kind of a notepad and a REPL at the same time, and it's the Scala kernel is a bit experimental. Uh, but then, in theory, if you have problem with anything, then you can stop me and I can go back to the source and try to execute it. But a note of warning is that it's experimental and so is Scala, so things may not be perfect. But I promise there won't be any more cat jokes since people are maybe allergic to them. So just this is roughly what I plan to cover. It will be mostly introductory stuff. I know that you have there's a range of people, so from like no function programming experience or knowledge at all to person who knows Scala Z. Um, so just if you're already familiar with the concepts, it may be a bit boring, but at least you will see how these things are done, say in the context of cats. So in particular, I will first start with some um, motivation why we care, and also summarize it if you wanted to use something like this at work. Uh, what risks that brings, or what applications you may find suitable. It will be a bit opinionated, but then I hope it'll give you some idea. Then I'll talk about type classes. So some of you are familiar with Haskell or Scala Z, in which case this will be a very boring part, but then if you're not, I'll just try to give you 101 on type classes. So it won't be a, I don't expect you will understand fully type classes, because at least in the, say, function programming course here at HQ, it's one lecture or two lectures, and this talk tries to cover it in, say, 10 minutes. Um, then I'll talk about functors and applicatives, which are sort of useful type classes if you want to operate on graph values or values with context. Then I'll talk about monoids, how to use them for sort of parallel operations, which is a topic maybe interesting for people who work on Spark. And finally, I'll talk about error handling in a sort of pure functional setting with options, XORs, and validated, uh, which are sort of useful type classes for this sort of thing. And I'll explain differences where you want to use one or another. All right, so this is what we discussed in the beginning, uh, before the actual talk. So Scala currently maybe suffers a bit from the split of community. So we have people who view Scala as this better Java. So it has a nicer syntax, it has many convenient features, but they usually don't try to utilize the more advanced features, and they may be afraid of them and so on. At the same time, you have people, say, coming from the Haskell background, and then they see Scala as this functional language, which is maybe a bit strange, but at the same time, very expressible type system, so they would try to write purely functional programs in it. And so there's this clash, and it has practical implications. So for code bases, you especially so cats are coming from this second sort of stream of Scala uses, uh, which brings some risks if you want to apply it. Um, what cats is about is that it's a collection of useful abstractions that you have in sort of pure functional programming setting. Java programmer would call it, say, design patterns. So it's something you want to use and reuse for robust code. But at the same time, it's something I don't expect you to be sort of experts after this talk. So it's something that you gain the intuition after you use it over and over again. So best way to learn it is to try it yourself. And these abstractions can be even useful in, say, in languages that are not purely functional. So here's like a blog post that talks about sort of like, I'm not sure if it will load, but then I'll try to post the slides later on. But it talks about like a sort of a business problem and how they approach it with category theory, so to say. Anyway, in this talk I won't talk about category theory much. I will rather do it from more practical approach, sort of how these abstractions can be used and applied. So I may say some imprecise things. So if you disagree with what I say, feel free to correct me. But I'll just try to put it in more layman terms, so to say. Now, CATS itself, I wouldn't call it directly to be a successor of Scala set. It's rather a different library. It has a bit different focus. If you look at the README or sort of the CATS web page, it has a bit vague statement of what it's supposed to be. That's why you may be interested in this talk, to sort of explore it. And in summary, it tries to be sort of nicer in many different meanings. One is that it should be more lightweight in terms of, say, performance overhead. So, say, Scala tries to be purely functional even in its own implementation. So internally, it for some things you may have a performance overhead that's may not be necessary, just because of the JVM wasn't originally designed for functional languages. CATS tries to be more pragmatic in the sense that, say, like internally, it may not be purely functional, but it will expose you purely functional sort of interface. So you as a user will still sort of do purely functional programming, but maybe internally it does some mutation. And another maybe important point is it tries to be more documented. Nowadays, I think Scala is also quite documented, but many years ago it was the case that Scala was some of the contributors had a feeling that type signature is the only documentation that's required, and many of the operators didn't have say English names, so there was only a few sort of ASCII characters, and it was kind of very puzzling for people to figure out. And there was also a reason why Scala became a bit controversial, and in some, say, corporate settings it was forbidden to be used. But then, note of warning, so even though it tries to be nicer, it's still sort of in development and quite experimental, so you won't say like things like Scala Stream, which is a thing that many people use Scala in a sort of a real production setting for. So these things are not ready, and it will take some time until CATS sort of evolves to this stage. But I'd say because of its goals that it tries to be sort of nicer and more documented, I think it's a good material especially if you're new to this. So looking at CATS is a good way to start and browsing the source code. And another point is that actually the things that you will learn from CATS, they are almost like one-to-one to things in Scala or spiral algebra or any of these sort of abstract mathematical libraries which have practical applications. And another thing is that so CATS is still evolving, and there are already, well, say like there's a iterative implementation that maybe came about a week ago, and there's this like a JSON manipulation, purely functional manipulation library. It's kind of like a fork of Argonaut that came, I don't know, like a month ago or 2 months ago. So there are sort of like practical things, but then they are still very new, so would be very risky to use it. Now, before you fall asleep and I continue with with the hard stuff, then I just like prepare sort of a summary for people who would be interested in using this in a real, say, corporate setting, it's a bit opinionated, so you may disagree with what I put here, but then I try to sort of say, uh, to sort of classify things. It's not just cats, but then all it applies to all libraries that provide sort of functional programming abstractions. Uh, so one thing is like a safe bet for this usage would be numerical computing or batch and stream processing. So people have been using these libraries for years and in settings, and there's good thing about this is there's a little overhead for learning. So even at Twitter, say they use Algebird, and in their experience, even people who didn't know anything about functional programming, they could still use it, and then it makes you have a type checking, so fewer errors in your say Hadoop code, and often it does some optimizations thanks to types, so your code is also faster. So it's kind of a really there might still it depends on like the nature of the task, but for many projects it's quite a safe bet. Then there's this middle ground where it really depends on the team, because this is what we discussed in the beginning. So there are, even though these things are nice, they have associated costs. So if you may have many people who only know Java, then they sort of resist learning functional programming. So you have the sort of training costs or overhead. You need to think about maintenance. You need to think about if you have a performance critical applications, these things may not perform as if you write very brutal mutable Java code. So this is kind of, it depends on the nature of the project whether to adapt them. And then there are sort of things that really, there are very cool blog articles about them, which is say this one, which talks about how you can sort of structure your code into um, using free monads, how to structure the effects and so on, which is, I personally think, very cool. But then I must say that even though the person who wrote the blog post says that they use it in production in their team, would be very hesitant to apply it in a, unless you have say a team of people who are experienced in Haskell and they are very comfortable with using free monads and so on. Any questions or comments? So let's now move on to the first topic, which may be boring to people who were already exposed to Haskell. So and so one thing to note, what does ad hoc polymorphism mean? So you may be familiar with the parametric polymorphism, which is usually something like this. If you have, say, a map function for lists, it works for all type A and all type B. So it takes a list of A, it returns a list of B, and that A and B can be anything. It could be integer, it could be other list, it could be string. So it's just kind of like parameterizing over the types. And in Haskell, there's a thing called type classes, which allows you to put additional constraints on these parameterized types. So in Haskell, you could, for example, write something like this, that you have a sort function, and then sort function takes a list of A to a list of A, but then it has this sort of constraint on A that you have, it has the order, some associated order, so it's kind of sortable, so to say, or comparable, that you have a compare operation on the type. So in some sense, it's a bit like Java interfaces, that Java interfaces also give you sort of a set of methods that the class that implements that interface should have. But it has some differences. So notably, so Haskell isn't an object-oriented language, so there's no associated object with it. Other thing is, if you have instances of these type classes, which means implementations of the type classes for some type, they are separate. So unlike in Java, if you implement an interface, you need to implement that interface within that class. So the code for that implementation of that interface needs to be in that class file. But with type classes, it's completely separate, so it could be anywhere basically, and which gives you some flexibility. And another point is that, well, before Java 8, interfaces couldn't have a default implementation. Nowadays they could, but then before Java 8, this used to be also a difference. And I won't have time to talk about it, but then they are very nice and sort of solve many. There's a whole paper that talks about, say, different sort of extensibility and integration problems that type classes solve. So they are, I think, a nice concept, but then it's not a feature, like a first-class feature in many languages, except for Haskell. But then in Scala, we have many other language features that allow us to emulate type classes very easily, namely, say, traits and implicit objects, which you could have seen before. So many years ago, people who would sort of like ad hoc do it, sort of write their own type classes and so on. But nowadays, there are nice libraries, and so if you look at the CATS implementation, it uses a simulacrum, which allows you to sort of write type classes without writing all the boilerplate about it. So, and there's also since it uses these implicit objects, there may be a sort of associated cost, but there's also a library that optimizes this away. So it's kind of, you can get this language feature for more or less for free in Scala. So let's look at how to use this in CATS. So here we import the order type class, in which case then it has some default implementations for common types, so we can then use it, say, for so we can then call like compare on directly on values it has for, and it's statically checked, so the both sides should be of the same type. So compare takes like two A's of the same type that are sort of comparable. So if you write something like this, you would get a compilation error. Now under the hood, there's like this trait order which has the compare method a to a, and then returns you integer which is -1 if one is less than the other, 0 if they are equal, and 1 if the other is greater than the first one. And then it gives you, and then implementation of this trait is then done through this sort of implicit through this instance. But then that's something you don't need to know about. The only thing to point out here is that in Haskell you could get these things automatically using deriving keywords. So if you have your own data type, you can just say deriving, show, ord, and so on, and it will give you implementations for free. In CAS, there exists this, it's still an experimental library, but then it's called Kittens, and that tries to sort of do this for you. So you can say you have this like class, case class cat, and it will already like derive you, say, like functors on it and so on. But that's what I'm not going to cover today, but then just to give you an idea. So, and why I talk about type classes is that most of the abstractions that are in CATS, they are type classes. So just they sort of emulate what in Haskell, many concepts that are part of the, say, Haskell standard library. And you can also find a thing called type classopedia, where all these things are sort of explained for Haskell. So now let's look into a more practical type class, or type classes, which are functors and applicatives. they allow you to operate on values that have some context. So here's the type class for functor. It has in Haskell this is called fmap, but then in cats and I think in Scala as well it's called a map. But you can, which may be a bit confusing because you may confuse it with the list map, but it's a similar thing, but it's kind of a generalization of that. So it's you take a value that is wrapped in some context, and then you take a function that operates on those values. So it takes something from A to B, and then you return a value of type B wrapped in the same context. What I mean by a context, here's an example of a context. It's an option you may know about. So option trade as two values, nothing. If there was, so I will talk about option at the end in more detail. But then this is a very simple one, and I think if you're familiar with Haskell, there's a data type called maybe. It's the same thing. So there's nothing if something went wrong and nothing was returned, or you have a sum which wraps some value of type A. So if and some cats give us an instance. They give us instances for many common data types, and option is one of them. So you could, if you import this, or maybe even without import. So, and I believe maybe in normal standard library of Scala, this may be possible. So you can call map on a sum with some value, say like +3. What happens is then intuitively that you have some value in a context here. It was a value 2 in this like sum box. Then the functor takes it away, applies the function, and then puts it back in the box. So you get the box value back. And then you may ask what happens if we have the other case, which is the empty or like none case. In this case, we get nothing back. So it's kind of, okay, we have no value. So nothing comes in and nothing comes out. And this is a fairly, say, convenient way to write it, that maybe if you didn't know about this, you may try to use pattern matching and sort of like manually unwrap all these values from the boxes, but then this is sort of general and works for any context. So say list is another box, and then for list the map instance or the implementation is the normal list map. So just like here, so you take a list of values, and then to each value you would apply this function +3. So you have here 2, 4, 6, you get 5, 7, 9, and you get like a list of these values back. So yeah, this is how it's done in Scala. So you can import syntax for functor, and here's one maybe a bit confusing example that also functions itself you get a functor instance even for functions, and you may ask what is then this, what does this do, right? So you have a function that takes one argument and then applies 3 for it, and then you map another function over it. So what happens? In this case, the map instance, you will see is just a function composition. So if you then have this new function and you apply it to 10, you get 15, because it +3 +2. It's like here. So this symbol is in Haskell and in Scala Z is for this map or fmap. So like originally you take a value in, you apply one function, you apply the second one that was composed, and you get the value back. Any questions? So now you may have a different case. What if you have so in that case we had the function wasn't in a box. It didn't have the context. So you may ask, what if we have a function that's in a box, and then we have a value that's in a box? How to apply the function from that box to the other one? Say something like this, that we have two options. One option contains is sum, and then function something plus 3, and then the other is sum2. In this case, we would need to use applicative. So in Haskell, all these things are in the applicative type class, but in cats, this type class is split into two. So we have the apply type class, and then we have the applicative, which extends apply. And the main stuff here is actually in apply. So the applicative itself, it just has this pure method that takes x and then returns it in box. So if it was the option case, then this would just, it would say pure 3 and it would return you sum 3. This is the more interesting thing. So this is basically what we want, as I described. So we want a value that's in a context, and then we want a function that's in a context, and get a value that's in that same context. So let's have a look how this works. Before we have a look, I just have here this small thing to help Scala compiler to figure out the types. It's just so I don't need to write like the things like sum and then also type annotation for the option. So it allows me just to write .sum on the values, and it would automatically wrap it, or just use this none. So here we have the case we sort of formulate the case I showed in the beginning. So we have function plus 3 in sum, and then the value 3, and then we use this apply, and we get that sum 5. So intuitively, what happens here is that so I described. So just this the illustrations I took are from a blog that tried to explain these concepts for Haskell. So just here it just means sum in the Scala world. So you have a function plus 3 wrapped in a context, and then you have the value plus 2. So if you use this app operator in Haskell, it's this weird operator. It will take the values out of the box and the function, apply them, and then put them back in the box. And interesting thing happens is that say the list constructor is also applicative. So if you, here's an example where we have a list of functions. So here's so there's a list that has this function times 2, and then this, and the second is plus 3, and we apply it to the list of these values 1, 2, 3. So this is what we are applying. So we have times 2 plus 3, and then applied with this 1, 2, 3. What happens is you get this Cartesian product. So it multiplies all these numbers by 3, adds 3 to them again, and then puts it together again in the list. So it's a bit powerful. Now, one thing we always did in these examples is that we always had one parameter on the other side. So it was always sort of one value. You may then ask what to use if you want multiple values, and then there are functions for that called like lift apply 2 and lift apply 3 and so on. But then there's more convenient way to write this. If you come from the Scala Z background, you may be familiar with this. So there's this operator, which many people give it in different names. So some people call it like Chelsea Bun or Admiral Akbar, the Scream, or Home Alone operator. And then this operator then allows you to write things like this. So we have it's still the there are still, you can write many things in this sort of applicative style. So you have a value, so you have these sum 3 and then sum 5, and then you apply this function which is like x minus y basically, and you get -2 back. Another thing is that say list appending is also a thing that takes two things. So one value here is the list with 4 wrapped in sum, and then we have here value 3 wrapped in sum. So if we map this, we get the list 3, 4 wrapped in sum back. So these were applicatives. Any questions? Now let's move on to different stuff. So monoids, they are something that may be simpler to grasp. So there are basically structures that can combine two things together. So you have semigroups, which has this combine that takes x and y and then returns you an element that's like a combination of these two, and monoid extends them with a neutral element. So this may sound scary, and I think I gave a similar talk or one talk a while ago, but then if you try to search for monoid, you get a lot of scary pictures on the internet, but it's not really that scary. So what it allows us to do is sort of like do things like monoids are everywhere. So here are just like a few examples of monoids. So say all the like numeric types are monoids. So like integers, if you sum integers, you get an integer back. If you have list, then this combine operator is a list concatenation. So if you sort of combine two lists, you get a new list with combination of the elements from both. Strings are also monoids. The options that we talk about are also monoids, and then the combination is done in a way that if you have nothing on one of the sides, it will return always the particle value. So, and if you have nothing plus nothing, then you get nothing back. Now, why I talk about monoids? Well, I think probably library to look up is Algebird, which is used all over the place, especially in say like Spark or MapReduce frameworks. And it's basically that monoids sort of give you guarantees that you want from this like distributed batch processing pipelines, or even real-time systems like Storm or Hummingbird. So one thing is that they are associative, so you can partition it and run it in parallel. So say like you can evaluate A on one node and then B plus C on different node, and then sort of combine them together. They are close, so if you sort of combine two monoids, you got monoid back. So you can do the reduction in multiple stages, and they also have the neutral element. So there's this sort of experimental code that has cats on Spark, in which case you would have these RDD operations. So for say for integer, well actually this is, so for every monoid you could use the normal combination. So basically for all these types, if you import cats, this wouldn't work. So if you need to sub numbers or combine strings or anything like that, then that's the way to go. Or you can also use different type classes, so we would use like minimum or maximum. But the main point is that, so these were simple examples of monoids, but then even more maybe complex structures are still monoids. So things like sets or maps or say Bloom filters, or different say logarithmic counting and so on. So these are things that you usually use in say big data settings that you can't fit all data in memory, so you'd probably use if you have a data set and you're only interested in orderings of the say you have you want to count I don't know, number of like exchange tweets between different users and so on, then there would be uh, big differences in, say, there would be some popular Twitter accounts that everyone follows and tweets to them, and there will be some, and then but then for most people it will be almost empty, so no one tweets to them. In which case, then there are orders of magnitude differences in this, and you have also many accounts. In which case, you could use one of these probabilistic counters for this, and they're already implemented for you in Algebra. So reason to use these is that it won't the whole thing won't fit in the memory, and you just say interested in like ordering what are the most popular words in some particular groups of people and so on. So these are, say, things to look at, and I won't say much else about them. Now let's look at error handling. If you come from the Java background, you know that Java's exception system that's fairly nasty. Another way to sort of do error handling is that you may set values return nulls. So both cases are not very nice. In Scala 2.11, there's this try data type that can help you to sort of capture it and do it in a nicer way. But it's still not ideal, so we'll look into more sort of approaches that are more appropriate for function programming. So we already talked about option. Let's look at this example where, say, we have this function half, which if you give it an even number, it will return you sum and then half of that number. And if that number is odd, it will return you nothing or none. So this is like what the graphically the function looks like. So it takes a value and returns you that value, returns you a new value in a context. Now you may ask the question, what to do if you have a value that's already that has some context? How to push it through this function? Any ideas? What you need? Yes. So you need a plunger, and that plunger is called a flat map in a Scala set or cats. So use flat map. So if you have like a sum 3 and you apply flat map with half, you get nothing back, none, as you expect, because this is an odd value. And then intuitively this what happens. So the flat map takes this value, then sort of plunges it through the function, and then you get nothing back. Now this is what happens if you have the even case, so you get the sum 2. Now if we have nothing, as you may expect, that there's like nothing goes in, nothing goes out, so it doesn't apply the function. And then flat map, normally this is the most scary thing in functional programming. So in Haskell, this thing is actually in the monad type class. In cats, it's again split into 2 type classes. So there's a flat map type class and there's a monad type class. The monad type class extends flat map with a pure function, which again just does what the pure for applicative did. And then intuitively, this is the operator notation for the flat map, or bind, as it is called in Haskell. So you take a wrapped value, something with a context, something like, say, sum 3, and then you have this function of this shape. So it takes a value and then returns you a value of a different type wrapped in something. And then the whole thing, the flat map, then returns this thing. So it's the value of type P wrapped in F. And then this looks very abstract, but then it's not that complex. So the hard thing about this is that this models all computation, which is hard to grasp. But then in cats, you just use it like this, and then you get also this bind operator. So a nice thing about bind is you can chain these operations together. So because every time you do a flat map, you get a wrapped value back. So if you apply flat map again, flat map expects a wrap value, so you can keep applying this. So here's an example where we start with the value 20 wrapped in something. We sort of plunge it to half. We get something back. We plunge it again to half. We plunge it again to half, and we get nothing back. Which is then like intuitively looks like this. So we have this 20 wrapped in an option. Option goes through the half. We get a 10 wrapped in an option. We unwrap 10, plunge it again through half. We get a 5 wrapped in an option. We take it out and put it back to the half, and we get an empty or like none option back. There's a different notation for this that you may be familiar in Scala, which is the for comprehension, or in Haskell you have a do notation. So to write something like this, you could write a for. We have this sum. We sort of plunge it to half. We get something. We get x1 back. We plunge it to half again. We get x2 back, and we plunge it to half again to x3, and then x3 is the thing we return, which is none. Any questions? No. So now let's look at some example, sort of real-ish example, how to do error handling in the functional setting. So we have this user class whose constructor is hidden. So it will give you this create factory method that you will provide it name, age, and email, and it will return you an option user. So if everything here is sort of correct, it will return you the user instance. If something went wrong, then it will return you none. And this is how you could write it. So these are just the validation things. So this scary looking regular expression just validates the email. So if the email is valid, it will return it in this option. This one validates age, just that it's greater than 0 or nothing. This one validates the name. If the name is not empty, it will return the name or return else. It could have been written differently, but then you can imagine that's just trying to motivate something like this you may have in a registration form or something like that. So then the actual creation here is using that for comprehension. So we have we validate name, we validate the age, we validate the email, and then at the end we return the user. So then this then works as expected. So here we create a user where we give an empty name and negative age and no email, and when we try to read the name of it, and actually we get the empty thing, we get none option. Here we have a sort of a proper username or like user, and age that's not negative, and a real looking email, and then we get back the name as we expected. So this approach is good if you have just one type of error, but then here in our example we actually have 3 different possibilities of error. So the name could be empty, the age could be negative, or the email could be invalid. So sort of a more functional ish way of handling this would be to create a data type to model these errors. So we would have, like, say, this class user error, and which has 3 cases. So we have this empty name case. If you have the empty string as provided as the name, then we have the invalid email that is the string, and invalid age if it was negative. And for that, if you're familiar with Scala, you may know that there's the either data type or either trait. But then problem with either is that I showed you the for comprehension. That was sort of like a neat way to write it. And then either from the standard library doesn't work with this because it doesn't have flat map. But cats and ScalaSet and so on, they have a thing called XOR, which you can think of as the right biased either with a flat map. So use it, just import cats data XOR. And then this is how we would change the code. So you can see that it looks almost exactly the same as with the option. The only thing we changed is now the types. So, and a little bit of code. So here, instead of the option string that was previously, we now have the user error or string. Here we have the user error or integer in case of the age, and user error or string in case of the name. Then this is exactly the same, but then the type. And before we had the sum or none, but here we use right and left constructors that give us the thing we need. So you see that if it's the left value, so the user error it's always left, and then the error construction or right with the correct value. Same thing here, same thing here. So, and then for the final thing, we again get a user error or user two, like new constructed. But the rest is exactly the same. So then when we do the instantiation as we had before, you can see that this one fails with the left value with the error empty name. And then the second one gives you the user as expected. So, any questions about? No. Now, you may have noticed that actually here the thing is that in this first example that's not just one error. Actually, this user is pretty messed up. So there's 3 errors in this constructor, and we only return empty name. And you may. So if you imagine this in like a context of a form where a user fills in a form and then gets error messages back, if this worked this way, then it would get sort of an error one by one. So you get the wrong name, you get, say, short password or something like that, which could be pretty annoying, and still there are forms like that. So instead, you may want to do print all the errors at the same time. In which case, we need to use a different type class. So these option and XOR, they're monads or flat mappable, how Java programmer would call them. So after a failure, they would short circuit and end. But then there's a type class called validated, which is an applicative functor. So you could do you can process all the events. So here's you import it like this, and then it has 2 constructors, valid and invalid. So here's a sort of a nonsense example how to use it. I guess you remember this home alone operator. So we have 3 values here, and then we apply it with a function that takes 3 arguments. So there's one event that is valid, and then this one is invalid, and this one is invalid. So what we get back is this invalid, and then there's a string that concatenates these 2 things together. So this is a pretty, let's say, silly example. So now let's look at how to use it in that user registration scenario we showed. And what we would like for that would be, say, like a list that would accumulate these errors. And one thing you know about in this scenario is that actually when you have an error and you would have a list of error, it's always non-empty. And cats for that gives you this class called non-empty list that sort of guarantees that the list is never empty, which is the ideal thing for this scenario, because you will always have an error, or it would, it may, I don't know what, maybe you could have an empty list if you had, say, another type of error that you didn't anticipate or something like that. But say in here we have all the errors sort of quantified. So again, the codes looks similar-ish as before, but then we changed the types. So here before we had the user error or XOR string. Now we have the validated, and then the left value is the non-empty list of user errors, and the value is the string in case of the valid email. Then here's the, again, non-empty list of user errors or integer, non-empty list of user errors or string. And the final thing is the same, so non-empty list of user errors or the user. So then this is then how it's constructed. So you don't use the for comprehension or like monadic syntax, but use this applicative syntax. So we validate name, validate age, validate email, and then if everything goes well, we would apply this with this sort of construct instance constructing function that takes 3 values and returns your user. So if we do it in our setting, so we have this fake user which didn't provide anything, so we would return you invalid. And here we have the non-empty list. So, and then the head is now empty name. Then we have a invalid age and invalid name. So sorry, invalid email. So it captured all the errors that we had. And in the second example, it's valid, so it returns you valid with the value we expect. Now, there's also there are many other things in cats. There's also a thing called type class called IR, which is kind of a hybrid between XOR and validated, which you may have another, say, scenario where you want to use it is if you have warnings and errors. So the behavior you want is that you would like to log the warnings and then print them all. But if you have some critical error, you want to short circuit and end the application and restart or somehow process the error. So there will be like scenario where to use IR. But then I plan to finish before 9, so I would stop here. And there are also many other interesting things in cats I didn't have time to talk about. I would recommend the tutorial I showed in the beginning. So there's a tutorial that follows, maybe if you search for cats on the internet you would find it. It's called Hardened Cats, and it follows a sort of old book series for Linux Scala Z. And it's sort of like day by day description of different things in cats. You can see that actually today we sort of covered. We went up to the sort of day 7, so like things that would take you 1 week to learn maybe. But well, we skipped a lot of stuff as well. So this is if you're interested in this, but then you didn't. So I don't expect you would grasp everything from this talk. So if you're interested, then this is, I think, a good resource to check out. And I will also, so I mentioned in the beginning that I prepared these slides in Jupyter, so I will try to post the code as well on the Meetup page. And in any case, that's more or less the end of the talk. So to sum up, cats are collection of abstraction for function programming in Scala. And today I covered type classes, sort of one-on-one introduction. I showed sort of useful type classes that you want if you have a wrapped values. So functors were the thing where if you have a function and a value in a context, and then you want to apply the function to that value in a context, then I talk about apply and applicative, which is the case where you have a a function that's wrapped in a context, and then you have a value wrapped in a context, and you want to sort of combine these two together. And at the end, we talk about error handling, which are examples of monads. There are many other monads, but in monads, this is the scenario. So you have a value in a context, and you have a function that takes some value of the same type and then returns you a new value in a context. Something like that. I briefly talk about monoids, which are sort of useful abstractions for combining things together in, say, parallel or distributed programming. And then we talk about sort of functional way of handling errors. That's, I think, all for the talk. Now